Let's look at exothermic reaction. Y-axis is H for enthalpy, heat exchange, and x-axis is reaction coordinate, some changes. We're going to start with the combustion reaction. Methane and oxygen reacts to give you CO2 and water in a complete combustion. So it goes, the energy change happens like going through a hill. For any reactant going to a product in an exothermic reaction, we'll have to have this passing this blue barrier. Okay, this one is starting from the reactant level to the hilltop. It's called the activation energy, or you can call energy of activation, right? And if I give some numbers, let's say 10 here, probably 20, 30, like that. So if I scale it roughly, so I can see this could be 30, then we can calculate the enthalpy change. Okay, so we need a unit kilojoule, kcal, something like that. So delta H shows the change of energy, that is written as H final minus H initial, enthalpy final minus enthalpy initial. So I put some simpler numbers so you can see what's going on. So the final is actually 10, the CO2 and water, and starting at 30 kilojoules, so difference is negative 20. So that makes this is an exciting heat, or I would say simply exothermic. Right? So it's a combustion reaction. All fuel molecules combust with an exothermic reaction. But you need to give this activation energy, which is the ignition. Okay? All right. So let's go to a bit complex one on the right side. It's the same axis I'm using, but I'm starting with 2 amino acid reactants making a dipeptide, or making a peptide bond. So reactant goes to product, and it's a very high barrier compared to your left side exothermic reaction. So endothermic reactions have high energy barrier, activation energy, high activation energy. So I would say this one as like a brick wall, so you can't simply jump over. You need a lot of energy to jump over. Okay, so that's the activation energy for this peptide bond formation, right? Or any other reaction that could be, okay? Now, so I'm thinking if I punch a hole in this energy barrier, the wall, and we can kind of go through this hole easier and reaching the product faster. It actually increases the both reactions, forth and backward. And this is called the activation energy catalyzed. So the yellow one should be called activation energy uncatalyzed, right? So we use catalysis to get the product fast, right? So the catalysis is a really important thing. Mostly we use metals like platinum and palladium, something like that, and it seems like it's bringing the activation energy down, but it never touch the enthalpy change. Okay, the identity of the reaction is not touched. Now the catalyst is not always metals. In the biological systems we use catalysis, but they are called unique proteins called enzymes. They are substrate specific. They're unique for pH and temperature for that reaction.